Welcome to Math with Professor V. In this video, I'm going to be working through and solving the most recent exam. I gave my Calculus 3 Multivariable Calculus class this fall. I'm not going to be going too much into the background or explanation of how to solve the problems. I'm just going to do it fast and furious. So all of the full-length video lectures that correspond to the topics covered are linked in the description for you to check out. Okay, I would say if you're using this video to like prep or study for an exam, I would pause it and try to solve all the problems before you watch me work through them. Okay, so here we go. First question says, find a non-zero vector orthogonal to the plane that goes through the points P, Q, and R. So just imagine we've got this plane here with 3 points P, Q, R, and we need some vector that's orthogonal to the plane. So pretty straightforward. You're just going to make two vectors that are in the plane. We can make PQ, PR, take their cross product, and boom, then we have a vector normal to the plane. So let's make a vector connecting point P to point Q. I'm just going to take coordinates of Q, subtract coordinates of P. So the components would be 2, 1, 3. And then let's make another vector, PR. Its components would be 5, 4, 2. And then we're going to take their cross product. That will yield a vector that is normal to both those vectors, and therefore that vector is normal to our plane. So their cross product will give me vector n. And then I just always do it in my head. So I imagine there's an I hat, J hat, K hat here, and then I just kind of cross these two out. 2 minus 12, that's the first component, negative 10. Next component, 11, and 3. Obviously, if you cross the vectors in the other order, then the signs would be reversed. So you could also have positive 10, negative 11, and negative 3 as an appropriate answer. Okay, find the area of triangle PQR. So we know that if we take the magnitude of this cross product, that will actually give us the area of the parallelogram that's determined by these points. Oop, that side's too long. So here. So P, Q, and PR determine a parallelogram. If I take the magnitude of that vector from their cross product, then that'll give me the area of that full parallelogram. I only want a triangle, so I need half of it. So the area of the triangle is going to be 1/2 of the magnitude of that vector from part A. So it's going to be 1/2 times the square root of 100 plus 121 plus 9. So this is going to be rad 230 over 2. Boom. Okay, last part of this problem says find the volume of the parallel pipette with adjacent edges PQ, PR, and PS. And then here the points are given. So we know in order to find the volume of the parallel pipette, all we need to do is take the absolute value of the triple scalar product. And since we're taking absolute value, then the order really is kind of not so important. So let me first create vectors to represent these edges. PQ has components 4, 2, 2. PR has components 3, 3, negative 1. And then PS, you have to use the same initial point, 5, 5, 1. Okay, now to get the volume, basically you just need to take the absolute value of the dot product of one of the vectors with the cross product of the other two. Okay, lots of variations allowed here. The answer comes out the same regardless. So let me just cross PQ and PR. Is that what I did? Negative 2 minus 6. Oh yeah, or any appropriate variation. So actually, I didn't do this one. I crossed PQ and PR. So PQ crossed with PR is going to give you negative 8, 10, 6. So then I'm going to need to dot those with PS. So, or you could say volume is going to be PS dotted with this cross product here, negative 8, 10, 6. Okay. So absolute value of, let's do that dot product, 5 times negative 8, that's negative 40, plus 50, plus 6, boom, 16. Okay, So the purpose of this first page was to make them not nervous and give them free points. Yes. Okay, next problem. Solve the problem. You must show all relevant work justification in order to receive full credit. Simply using a memorized formula will result in a score of 0. So let line 1 be the line through the origin and the point 2, 0, -1. And then let line 2 be the line through the points 1, -1, 1, and 4, 1, 3. Find the distance between line 1 and line 2, and the lines are skewed. So just think they're like in different planes. Here's line 1, and then line 2 somewhere over here in another plane. Let me at least make it straight. Okay. So here's the thing to remember. Anytime you're trying to find the distance between two objects, you're going to need to connect them, right? So let's go ahead and do that. So let's connect them. How do I do that? I need a point, right, in each of these lines in order to connect them. So I'll say I have a point P here, and then I have a point Q here. All right, great. What should I use for point P? I'll use the origin, 0, 0, 0. And then what should I use for a point here? I'll just use this one. It's so nice. Q, I'm calling 1, -1, 1. I'm going to connect P to Q. Great. So PQ has components 1, -1, 1. Okay, now most likely, since I'm just picking a point on each line willy-nilly, I didn't connect them so that this vector is orthogonal to both of them, thus yielding what the distance is. When we say distance between two lines, we want the shortest distance, right? So what do I need to do? Well, I need to somehow project this vector in a direction that's orthogonal to both of these lines. How can I do that? Well, if I have the direction vector for line 1 and the direction vector for line 2, and I take their cross product, that new vector is mutually orthogonal to both their direction vectors. Then all I need to do is project this vector along that normal. So here we go. Do I have the direction vector for line 1? Yes, because it goes through the origin and 2, 0, -1. So I'll say V1, direction vector for line 1, has components 2, 0, -1. What about line 2? Do I have its direction vector? I can find it, 4, 1, 3, and 1, -1, 1. Its components would be 3, 2, 2. Good? Okay, so if I take their cross product, V1 crossed with V2, I get a vector that's orthogonal to both. So then I would end up with 2, -7, 4. Now to find the distance between the two lines, what I want to do is take PQ and project it along this vector here. This vector, shall we call it N? Yes. Okay, and then just in case one of these is longer than the other, right, I'll just take absolute value to make sure everything's positive. So scalar projection of vector PQ along N, which is going to be their dot product, 1, -1, 1, dotted with 2, -7, 4, divided by magnitude of n, which would be square root 4 plus 49 plus 16. Okay. All right, and then from here, let's take the dot product. So in the numerator, we're going to have 2 plus 7 plus 4 over square root. That's going to give us 20 plus 49, 69. So this is 13 over square root 69. All right, there you go. We did this one in class so many times. Okay, determine whether the lines L1 and L2 are parallel, skew, or intersecting. If they intersect, find the point of intersection. So first, let's address whether or not they're parallel. What's the direction vector for line 1? It has components 2, -1, 3. I'm just looking at the coefficients here. And then what's the direction vector for line 2? It has components 4, -2, 5. So notice these direction vectors are not scalar multiples of one another. So therefore, the lines are not parallel. Okay, the next thing I want to check is, are they intersecting? Meaning, do they have an ordered triple XYZ in common? So if that were to be the case, they would have an X coordinate in common. So 3 plus 2t would have to equal 1 plus 4s. they'd have a y coordinate in common. So 4 minus t would have to equal 3 minus 2s. And similarly, 1 plus 3t would have to equal 4 plus 5s. Now we have a system of 3 equations and only 2 unknowns. So I'm just going to work with the first 2 equations and solve from here and then see if that solution satisfies the third equation. Immediately something wild happens. Let me rewrite the top equation as is. 3 plus 2t equals 1 plus 4s. And then I'm going to double the bottom equation. So 8 minus 2t equals 6 minus 4s. And if you notice, all my variables cancel out, and I'm left with 11 equals 7. Well, that's certainly not true. That's as false as it gets. So what does that mean? That means there's no solution to this system. Therefore, the lines do not intersect. There's no point of intersection. There's no order triple that will satisfy this equation. So since the lines are not parallel and not intersecting, then that means they are skew. Okay, good. I don't know, some people found a point of intersection. They did some really wild illegal algebra. The math police have fetched them by now. All right, next one. Find the equation of the plane that passes through the point 3, 5, negative 1 and contains the line that's given there. So here's what's going on. We need the equation of a plane. Anytime we write an equation of a plane, we need a vector normal to the plane and we need a point in the plane. Well, they gave me a point, 3, 5, 1. Here's my point P. Also, they told me this plane contains this line here, this line. I'll call this line L, okay? Well, I need a vector that's normal to the plane. How do I make a vector normal to the plane? If I take the cross product of 2 vectors that are in the plane. And they've given me enough tools to do that. The direction vector of this line is in the plane. The direction vector of the line is in the plane. The direction vector of the line has components -1, 2, -3. All I need now is one more vector in the plane, and then I can cross it with V and get a vector that's normal to the plane. Well, take a point that's on the line. I'll call it Q. I'll just plug in 0 for t. Q has coordinates 4, -1, 0. Can you make a vector now? Let's go from Q to P. That would come out nicer. And that has components 1, -6, +1. Yes? So here's a vector from Q to P. Okay, what I need is a vector normal to the plane, and I can get that by taking V crossed with the vector from Q to P, which is going to give us 8, 1, -2. I won't bore you with the details of the cross product. Okay, now all we need to do is form the equation of our plane. So here's a vector normal to the plane. You can use the point P that was given. You can use the point Q that you found from the line. It really doesn't matter. Math is so beautiful, it'll all work out. So we have 8 times x minus 3 plus 1 times y minus 5. I'm using the given point. Minus 2 times z plus 1 is 0. And then this will all clean up to 8x plus y minus 2z is 31. Perfect. Okay. Question 5. Sketch and identify the given surface. Include traces in each of the 3 coordinate planes. Your graphs must be neatly labeled in order to receive full credit. So right away I can recognize this is the equation of an ellipsoid and they needed to identify the surface. Let's put it in standard form. I'm going to divide the entire equation through by 36 so it's equal to 1. So I'll have x squared over 9 plus y squared over 4 plus z squared over 1 equals 1. Let's do the traces in all the coordinate planes first. So in the xy plane, z is equal to 0. So if I substitute in 0 for z here to the ellipsoid's equation, I'll get the trace in the xy plane. So we have x squared over 9 plus y squared over 4 equals 1. That's an ellipse, hence this is an ellipsoid. We're very wild with how we name things in math. So in the x direction, the intercepts will be at plus or minus 3, and in the y direction, plus or minus 2. Great. Then we can do a trace in the yz plane. We would need to set x equal to 0 to obtain it. And we'll get y squared over 4 plus z squared over 1 is 1. So I'll call this the y-axis. This is the z-axis. And let's see, y is 2, and z has intercepts at plus or minus 1. There's another little baby ellipse. And then lastly, we can do the trace in the xz plane. I obtained that by setting y equal to 0. So we'll get x squared over 9 plus z squared over 1 is 1. So I'll put the x and z axes here. X-intercepts are plus or minus 3, the square root of the number in the bottom. And then z-intercepts plus or minus 1. So now all I have to do is draw these 3 traces and then put together my ellipsoid, okay? So in the x direction, the intercepts are going to be at plus or minus 3. And then for y, where are they? Plus or minus 2, negative 2. And then for z, they're not very big, 1. But I'll just spread it out so we don't have like just the most squished graph in the planet. Okay, so here's a trace. Then here's another trace. That's xz plane. And then lastly, I need this one in the xy plane. So there should be 3 total. And you can just add some shading. That's good enough. Okay, I was pretty lenient with the grading. Next question, probably the most difficult one on the exam. At what point does the curve have maximum curvature? And what happens to curvature as x approaches infinity? In this case, f of x equals e to the 3x. So our formula for curvature when you're given a function of x is absolute value of f double prime of x over 1 plus f prime of x squared. And this is all raised to the 3/2 power. Okay, so thankfully we just have e to the 3x. So finding f prime and f double prime is relatively simple. F prime of x is 3 e to the 3x, and f double prime of x is 9 e to the 3x. So my curvature is going to equal absolute value of 9 e to the 3x. I don't need absolute value, it's not negative. Over, hold on, that's so crooked. Over 1 plus 3 e to the 3x squared, all raised to the 3/2. So this will simplify to 9 e to the 3x over 1 plus 9 e to the 6x to the 3/2. Okay, so in order to see where the curve has maximum curvature, I need to find where this function has a maximum. So think back to Calc 1. How did you find local extrema? You would take the derivative, get your critical points, do the first derivative test, and determine from there. So I need to take the first derivative so I can get my critical points. And yes, we need to use the quotient rule. So here we go. We've got low d high, so derivative of the numerator would be 27 e to the 3x, minus high d low, 3/2, 1 plus 9 e to the 6x to the 1/2, and then don't forget chain rule, derivative of the inside is 54 e to the 6x, over low low. So squaring the denominator, we have 1 plus 9 e to the 6x cubed. Okay, to simplify from here, you want to factor out the greatest common factor. I can take out 1 plus 9e to the 6x to the 1/2 power only. And then I can also take out, do you notice, a 27 e to the 3x? Yes, yes. And also, like, we can cancel this 2 with the 54, make it 27, okay? So just take that 27 out, and this e to the 3x, everybody else stays. Don't try to multiply it out. You won't get anywhere. It'll just turn into a hot mess express. If you need help on how to simplify an expression, your derivative, after doing the quotient rule, I have a video just on that, because in Calc 1, so many students have a rough time, not with the calculus, with the algebra. Okay, so when I've taken out 27 e to the 3x, 1 plus 9e to the 6x to the 1/2, I'm just going to have this factor to the first power, so I'm just going to leave it like that. And then what's left over here is minus 27e to the 6x, okay? over 1 plus 9e to the 6x cubed. And then I can cancel this since it's the same factor as the denominator. This is now to the 5 halves. And we'll have 27e to the 3x times 1 minus 18e to the 6x over 1 plus 9e to the 6x to the 5 halves. So there's my derivative. So in order to see where we're going to have a max, I need to get my critical values. And that happens when the derivative is 0 or where it doesn't exist. There aren't any places where it doesn't exist because the denominator is never going to be 0. And it's not possible for 27e to the 3x to be 0. So I'm only going to look where this factor here equals 0. So kappa prime means that 1 minus 18e to the 6x is 0. That happens if e to the 6x is 1/18, which happens if x is 1/6 natural log 1/18. So there's a critical value. Now we can't assume all our critical values are extrema until we do the first derivative test. I mean, you could do the second derivative test, but I don't want to take another derivative of that thing. So you put your critical number on the number line, and then you can test with whatever values you like that are in the domain of the function. In this case, we're fine. You test in your first derivative the sign here on this side on somewhere smaller than the critical value and somewhere larger. Now, you don't need to plug in your test point into this factor because it's always going to be positive. Same goes for here. So you're only plugging the test points into this factor here, the one I've highlighted in yellow. Anyways, on this side, the derivative's positive, which tells me my function's increasing, and on this side, it's negative, so it's decreasing. So that tells me, yes, indeed, we get a local max. So we have a max at x equals 1/6 natural log of 1/18. And then the problem did ask for what the point was. So I need the function value. So I need f of 1/6 natural log of 1/18, which is e raised to the, it was 3 times x. So 3 times all of that is going to be 1/2 ln 1/18, which simplifies to 1 over 3 rad 2. Okay. Good. So that's the first part of the answer. No, we are not done. The second part said, do you see? What happens to curvature as x approaches infinity? So I need to take the limit as x approaches infinity of the curvature function. So now we're going to look at what's the limit as x approaches infinity of 9e to the 3x over 1 plus 9e to the 6x to the 3 halves. Well, I have an indeterminate form of the type infinity over infinity, so we can go ahead and use L'Hopital's rule. So this is the limit as x approaches infinity. Derivative of the numerator is going to be 27e to the 3x. The denominator, be careful, chain rule time 3 halves, 1 plus 9e to the 6x to the 1/2 times 54e to the 6x. Then you call your cleanup crew. So this will cancel, this is a 27, and then now this will just be e to the 3x. So we've got limit, x goes to infinity, just 1 now, right? Over 3 times 1 plus 9e to the 6x to the 1/2 with an e to the 3x. All that really matters is, this is going to infinity. I have a constant over infinity, so this limit is 0. Perfect. Alternatively, if you just think about it, heaven forbid we think about something, f of x is e to the 3x. You know what e to the 3x looks like, right? I hope. Yeah. Exponential function, steeper than normal e to the x. What happens to the curvature as x goes to infinity? It's basically looking like a line. So the curvature approaches 0, if you just think about it. Okay, this was definitely the trickiest problem for most people. Next, 7. Actually, they messed up 7 a lot too. 7 is so important for later in the semester. So if you need help, make sure you get these ideas down. If you need an extra video on this topic, on the topic, you know, like the chapter 7 entails, let me know. So at what points does the curve intersect the paraboloid? So this curve here is a vector valued function, r of t. Let me write it in component form. So we would have t0, 2t minus t squared. And I want to know, where does it intersect the paraboloid? Z equals x squared plus y squared. I'm just going to substitute in the components of the vector valued function into the paraboloid's equation. So z would be 2t minus t squared. X is, it's right here, guys, it's t squared, and y is 0 squared. Okay, then we solve this. So we would have 2t squared minus 2t is 0. So factor out a 2t, and we're left with t minus 1. So this happens when t is 0 or 1. The amount of people who just didn't have the algebra skills to solve this was shocking. From here, we have to figure out the points where the curve intersects the paraboloid. So how would you do that? I need an x, y, z coordinate that corresponds to each of these values of t. I think the cleanest thing is just come back to this vector valued function. So if t equals 0, we get the point 0, 0, 0. And then if t equals 1, we get the point 1, 0, 1. And that's it. That's all there is to it. Okay, part B, find a vector function. So basically we're finding r of t that represents the curve of intersection of the cone and the plane. Okay, so we're gonna have to equate these two surfaces basically. Easiest thing is, since z is isolated, to set those equal to each other. So square root of x squared plus y squared equals 1 plus y. I'm on the hunt to isolate one of the variables so I can identify my parameter. Let me square both sides. That seems like the way to go. And so we'll have x squared plus y squared equals 1 plus 2y plus y squared. Ooh, thankfully y squared cancels out. And then you have to make a decision. Should I solve for x or y? The answer is y, because if you solve for x, you're going to have plus or minus a square root. And we don't want to give a vector equation that way, because one part's going to represent the positive, one's going to represent the negative. No, that's too messy. So we have right now x squared equals 1 plus 2y. We're solving for y. Yes, we are. So y equals x squared minus 1 over 2. Most obvious choices then, let me let x equal t, my parameter. Y would be t squared minus 1 over 2. And then how do I get z? Plug in what you have for x and y into either equation. This is the nicer one. Math is hard enough. Don't make it harder for yourself. So z equals 1 plus y. So 1 plus t squared minus 1 over 2. Which is going to be, yes, 1/2 t squared plus 1. Plus 1/2, excuse me, which you could write as 1/2 t squared plus 1. Okay, so then just put it all together. So r of t is t, 1/2 times t squared minus 1, and then 1/2 times t squared plus 1. Good? Okay, perfect. Moving on, only two more. Find the arc length parameter along the curve from the point where t equals 0 by evaluating, and I know I gave them the formula. They should know it without me having to give it, but I just took mercy on them. Okay, so here's r of t. If you want to rewrite it in component form, maybe that's helpful. So r of t equals e to the t cosine t, e to the t sine t, and 7e to the t. So remember, v of u, magnitude of v of u is the same as magnitude of r prime of u. So we need to take r prime, clean it up, find its magnitude, and then set up our integral. I would do all that first. Okay, r prime of t, we got to use product rule, so it'll be e to the t cosine t minus e to the t sine t, e to the t sine t plus e to the t cosine t, and then lastly 7e to the t. Now to get the magnitude, first thing I notice is like, ooh, I can factor out e to the t from everyone. So let me do that. It'll make finding the magnitude much easier. It's not mandatory, but highly recommended. How about that? So then magnitude of r prime of t is going to be absolute value of e to the t, which is just e to the t, and then you do the magnitude of the rest. So you'll have cosine t minus sine t squared plus sine t plus cosine t squared plus 7 squared. So just leave that e to the t outside. It's minding its own business, letting us focus on the rest. Cosine squared t minus 2 cosine t sine t plus sine squared t plus, multiply out the other one, sine squared t plus 2 cosine t sine t plus cosine squared t plus 49. Okay, and then, magically, not so magically, these terms cancel out. And then we have 1 plus 49. So 2 plus 49, we have square root 51. That's r prime of t. Okay, perfect. So then s of t is going to be integral 0 to t. You can't have the same variable in the integrand as one of your limits of integration. So we have to swap it out. E to the u rad 51 du. Easiest integral, right? Antiderivative of e to the u is e to the u. Evaluate from 0 to t. So then we could say now s of t equals, just leave the rad 51 out, e to the t minus e to the 0. Done. Okay. Last one, I told you I'm solving this fast and furious. For the curve r of t, find an equation for the indicated plane at the given value of t. So here's r of t. Let me rewrite it in component form. And we're asked for the equation of the oscillating plane. So you need to remember which vector in the TNB frame is normal to the oscillating plane. And the answer is the binormal vector. So here's the important thing. We don't actually have to find the components of the binormal vector. All I need is a vector that's normal to the plane. So any scalar multiple of the binormal vector will work. And we know the binormal vector is equal to our unit tangent crossed with our unit normal. Well, we obtain the unit tangent by taking r prime dividing by its magnitude, right? And then the unit normal is t prime divided by its magnitude. Essentially, this is first derivative of r crossed with second derivative of r, because I'm taking another derivative. So my binormal vector is equal to c some scalar times r prime crossed with r double prime. This vector right here is normal to the oscillating plane. Therefore, it's good enough to use and a lot less stressful to find than the actual binormal vector. Making sure these are unit vectors is not essential when finding the equation of a plane. I just need any vector normal to the plane. So all I have to do is take r prime, cross it with r double prime at 0, and then use that for my normal. Okay? Good. So r prime of t, first derivative is going to be 40 over 9 times 3 halves. So we'll have 20 thirds times 1 plus t to the 1 half. Next component, don't forget 1 minus t. When you do chain rule, that'll be negative 20 thirds, 1 minus t to the 1 half. And then last component's 10 thirds. So r prime, they told me at t equals 0, would have components 20 over 3, negative 20 over 3, 10 thirds. Now, I'm going to cross this with r double prime at 0. And I just need something parallel to b. It doesn't have to exactly preserve the length, right? So instead of all these ugly fractions, guess what I'm going to use? I'm going to use 2, negative 2, 1, and have the most relaxing cross product ever. Just you watch. And then r double prime of t, so I'm going to take another derivative now from here, would have components, let's see, 10 thirds times 1 plus t to the negative 1 half, positive 10 thirds now times 1 minus t to the negative 1 half, and 0. R double prime of 0 has components 10 thirds, 0. You think I'm going to use that for my cross product? No way. 1, 1, 0. That's where it's at. So I'm going to cross these two vectors. They are scalar multiples of r prime of 0 and r double prime of 0. So their cross product will give us a vector that is still normal to the oscillating plane. But look, I can cross them so easily. Negative 1, 1, 4. Okay, that's cute. Instead, though, we want the x always positive, so I'm going to use 1, -1, -4. If they didn't do that, it was fine. I just like to do it for cleanliness purposes. Okay, so that's my normal vector to the plane. That's parallel to the binormal vector. Good enough. I can use it for my oscillating plane. And then I need a point on the plane, so you get that from the original vector valued function. So even though, you know, it gives you a vector quantity, we just use it as an ordered triple. 40/9, 40/9, 0. So here we go, put it all together. Oh, 1x, right? Times x minus 40/9 minus 1 times y minus 40/9 minus 4 times z minus 0 is 0. And you just get x minus y minus 4z is 0. And that was it. Let me tell you, some of them did some wild stuff. So scaling things down can really help with your computation and eliminate, you know, careless mistakes that also arise. So that's it for exam 1. I had a request from them to do more examples of limits in multivariable calc. So I'm working on that. I'll get that out this week. And if there's anything else that you have requests for, because I've got a few comments that I don't have enough Calc 3 videos compared to my library of Calc 2 and whatever. Yeah, that's definitely true. So give me specific topic ideas that you guys are struggling with so I know exactly what to create for you all. And like I said, this was crazy, fast, and furious. I mean, like, I didn't explain much and I went like Speedy Gonzales through this. So all the video lectures for these sections are linked in the description. If you found this video helpful, don't forget to give it a thumbs up. Leave a comment down below. Did you take your first Calc 3 exam? And don't forget to follow me on Instagram and TikTok, Math with Professor V. Bye, guys.